Welcome back to Decaf-Math ASMR, and welcome if you are new here. I hope that you're doing very well. Today I am going to be serving you an integral, specifically this integral, x cubed over the square root of 9 minus x squared with respect to x. And we will be looking at this two ways, like eggs or something. But I thought that this would give us an opportunity to practice some of the tips and techniques that we have in our math toolbox or math caboodle, or wherever you store all of your knowledge about integrals and all of the techniques that you've developed over time. So we are going to use some algebra to break this up a little bit. We will use some U-substitution, and I picked this question because I've seen it in a couple of different contexts. So we will also be able to practice some trig sub, and I know that especially for trig sub, a lot of times when it's first introduced, it can feel like it just comes out of nowhere, and then the next thing you know, you have a bunch of formulas to memorize and when to use which substitution, and you just have these rules. So I'm hoping that by going through this step by step together, it can help us build some intuition behind why we're doing what we're doing. So we will do this two ways, and let us start with the slightly shorter one. Well, actually, I'm thinking it'll be a lot shorter, and this way I don't scare you off right from the start. So we are going to start with U-substitution, and I'm going to use algebra. So first of all, don't forget we have our basic integrals, which is basically anything you could find on an integral table. All of our derivative counterparts. We have our trig integrals, inverse trig. We have hyperbolic trig, inverse, all of that stuff. So we have integration by parts, U-substitution, and sometimes we have to mess around with it a little bit to get it in the form that we want. So the reason I'm thinking U-substitution is good here is because if I were to break this x cubed up into an x squared times x, then I have a piece of a du. If I were to have a u that's like a squared part, then the du would be a linear thing. So it seems like we would have the pieces here. And so if I were to let u equal 9 minus x squared, if you remember how U-substitution goes, it's okay if you don't, but if I were to let this little piece be u, then we also want to make sure a piece of our du is in this so that we can convert dx into du. So if I had u is 9 minus x squared, then du is the derivative of this, which is negative 2x dx. And that's a good thing because we have our x dx here, which is this part. We have that taken care of because this is basically my du over negative 2. And then under here we have our square root of u by our choice of u, and then the top is our x squared, which is fine. We can rewrite this in terms of u as well. So x squared is 9 minus u. If I use some algebra and flip, flip, flop, flip, flop, flip, flop, flip, flop, that's okay. So we have x squared is 9 minus u. So now let's just go ahead and carry out this substitution. So we have the integral of 9 minus u over the square root of u, and then this x dx is actually du over -2. And so I'm going to go ahead and make this negative go up here and pull out the half because the 2 is on the bottom. So by putting the negative, I just like having the variable first. So u minus 9, because we're distributing a negative. So -9 plus u, which is u minus 9 over the square root of u. And then we can distribute this square root of u on the bottom here and here, and it only works if we have it in this order, where we have the something minus something on the top, and the bottom thing is 1 unit or 1 term. That's, we can distribute like this because of the distributive property, but it doesn't work the other way around. We can't, if the u minus 9 is on the bottom, we can't distribute this way unless we treat the u minus 9 as a single term as well. Okay, so now we're just continuing with the algebra here. We have u over square root of u minus 9 over square root of u, all with respect to u. So we've translated our entire integral with respect to x into an integral with respect to u. So now I am going to write this as 1 power. So u to the 1 divided by square root of u is u to the half. So it's u to the 1 minus 1/2, which is just u to the half minus 9u to the -1/2. And I'm writing it this way so that we can use our integral table or integral rule, that if we have a variable to the n, the integral is going to be u to the n plus 1 all over n plus 1. That's our integral version of the derivative, right? So so u to the half plus 1 is 3 over 2. Divided by 3 over 2 is the same as multiplying by 2 over 3. Then minus 9 times u to the -1/2 plus 1 is 1/2. Dividing by 1/2 is the same as multiplying by 2. And then don't forget the plus c. Good. And then we can just go ahead and distribute this half back in if you want to, just to clean it up. And so we have half times 2 is just 1, and we have u to the 3 over 2 over 3 minus 9u to the 1/2. And this is our answer. But we want our answer in terms of x because our original question was in terms of x, and our u is just a random substitution that we use to make our lives easier, but it doesn't mean anything until we plug it back. So we know that we made this substitution, that u is 9 minus x squared. So I just go ahead and plug in 9 minus x squared everywhere that I have a u. So 9 minus x squared to the 3 over 2 over 3 minus 9 times 9 minus x squared to the 1/2 plus c. And that is it. That is our answer for this integral. And assuming we did our calculations correctly, this should be all that it takes, is just one u substitution with a little bit of algebra play here. Now, the other method is to use some trig substitution, and I did want to make this point. So a lot of times, once we learn trig substitution, it is very tempting to just want to use it everywhere. So every time we see this form that we have the square root of some number minus x squared, so once you learn when to actually apply it, it's tempting to always just want to jump straight into using it. But sometimes with a little bit of reordering the question, it depends on the question. Sometimes it is easier to just use one of the other tricks that we already know. But in this case, we are going to practice trig sub anyway. So we are going to tackle this question with the sign substitution, which if you're a formula person, since we have this form in our question, we have an a squared, so some kind of number squared, minus a variable squared. In this case, we have square root of 3 squared minus our x squared. Then the substitution that we are going to make is to let x equal 3, which is this a, not a coincidence, 3 sine theta. And in general, it'll be a sine theta. And so for u substitution, we try to find a u that simplifies our question, right? We let a u, we want a piece of du, and we want that to simplify. We want u in terms of x. But if you notice here, if we let x equal 3 sine theta, we are going to be, when we do this substitution, it's going to expand it. And temporarily, it's going to get a lot messier. However, if we are clever, and this is the whole point of our trig substitution, is that if we are clever in how we choose to expand this, once we apply trig identities, this should then simplify back down. And we get rid of the square root of 9 minus x squared thing, because that's kind of our trouble area with this integral in the first place. So let me show you how it breaks back down. So if I make this substitution that x equals 3 sine theta, then basically we just put that everywhere we have an x, so 3 sine theta cubed over the square root of 9 minus 3 sine theta squared. And then we have a dx. So if x is 3 sine theta, then dx is going to be 3 cosine theta d theta. Just the derivative of this, and the derivative of sine theta is cosine theta. The constant just gets pulled to the side. So we also substitute that 3 cosine theta d theta. So we translated our integral into from x into a stuff with thetas, and like I said, this looks so gross right now. We have square roots, we have cosines. Now why on earth would we do this? Well, if we look at the bottom specifically, this part, this is our magic key. So if I were to just focus on the bottom, I have a 9 minus 3 squared is 9 and sine squared theta. So I can actually factor out the 9. So 9 times 1 minus sine squared theta. And then I can pull out the 9 from the square root, right? Because it's square root of 9 times the square root of this stuff, which is 3. And this is exactly what I'm after. This is basically a piece of one of our trig identities, and this is what gives away the fact that we are going to use sine for this. The identity is that cosine squared theta plus sine squared theta equals 1. So if I rearrange this to try to look for the square root of 1 minus sine squared theta, I can move this over here. I can solve for cosine. I have to do a plus or minus root though, because I have a cosine squared theta. So I just rearrange this. this looks awfully like the square root of 1 minus sine squared theta. I just have a plus or minus here, which is fine. If I want to directly make it 1 minus sine squared theta, which is the positive root, then I need to put in an absolute value of cosine. Technically, cosine theta could be negative, right? It depends on where you are on your unit circle. Cosine is your x coordinate, so anywhere from here to here will give you a negative cosine. But for the sake of an indefinite integral like this, we don't have bounds, so we can just assume that this is cosine, just positive 3 cosine theta, okay, without the absolute value. However, if you do have bounds in your question, and we can come back and do more practice problems like this for our other substitutions as well, you may need to split your bounds or your integral into pieces where you subtract the part where cosine is negative so that the negative negative becomes your absolute value, becomes your positive, and then you keep the positive part. So this absolute value part may become important if you have bounds. But for now, since we don't, we can, and it is safe to assume that we have positive cosine. So anytime we have the square root of 1 minus sine squared theta, we can just put in cosine, which is why we picked a sine theta. So our bottom now becomes 3 cosine theta. So let's carry out the rest of the substitution then. We have the integral of 3 cubed is 27 sine cubed theta over, like we said, this all boils back down to 3 cosine theta, and then times 3 cosine theta d theta. And now this is so beautiful, so glorious. We can cancel out the 3's, we can cancel out the cosine, and this is the whole point of making it complicated and then simplifying, because this mess of a thing boils down simply to the integral of 27 sine cubed theta d theta. Now at this point we need to actually evaluate this integral, but it is much simpler than this. So this is probably a nice little pausing point because we have completed the actual trig substitution part. So if you get something like 27 sine theta d theta, so like this is more complicated just because of the nature of this question, but sometimes you'll just get an integral that you can directly do. In this case, we need to now, and this was my excuse, to practice what to do when we have powers of trig. So this is just another tool, and we're going to continue to carry out this integral. But I did want to note that this part is only more complex because of this question, but not all trig substitution questions involve this many steps. Okay, so now we're going to practice what to do with this. So we have the integral of 27 sine cubed theta d theta, and since we have an odd power here, we are going to basically try to break this down into squares of sine, because we know that sine squared theta is 1 minus cosine squared theta, just a rearrangement of our sine squared plus cosine squared equals 1. But I'm going to try to do a U-substitution. So I'm going to break this up into a sine squared theta, which is something with cosine, and then I'm going to reserve a single sign here on the side so that I can do the U-substitution, so that the derivative of the cosine part is going to have my sine theta d theta in it. So this is like a little algebra trick that we can do when we have an odd power of a trig function, or sine specifically. So we'll do 1 minus cosine squared theta sine theta d theta And then if I let u equal cosine theta, so that I have here, I have the 1 minus u squared, then du is negative sine theta d theta. And since I have a sine theta d theta, that's basically negative du. And so this negative, I'm just going to plop here and flip the order. Negative 1 minus negative 1 plus u squared, so u squared minus 1. So the integral of u squared minus 1 du. So with this little algebra trick that I have here, I basically make it so that we converted from theta to u. And now we have 27 times u cubed over 3 minus u plus c. So this is one of our basic integrals. So this is our answer, but it's in terms of this u. And our original question was in terms of x. So we have to go from u back to theta, and then from theta back to x, so that we can answer our actual question, okay? So from u to theta is not so bad, because we literally have that we set u equals cosine theta. So everywhere that I have a u, I just put cosine theta. So 27 times cosine cubed theta over 3 minus cosine theta plus c. And now we need to go from this theta thing back to x. And the only relationship that we do have is that x equals 3 sine theta. So that's all that we can really say, but we can do a little more with this. So that means that x over 3 is sine theta. So here you can use your trig identity here to solve for cosine, because we have a cosine theta cubed here and a cosine theta. So you can, if you like algebra, you can go ahead and do that. So solve for your cosine and then put in x over 3. But since we can basically think of this as doing an inverse sine and then taking a cosine of the inverse sine, we can draw this cute little right triangle. And so I'm gonna fill it in. It's the same thing, so it depends on if you like pictures or if you like algebra. But I'll just show you this way. This is based off of our SOHCAHTOA. So sine of theta is opposite over hypotenuse, and so this is a ratio, and we're going to take the basic triangle, but it's okay if we scale everything. It's all a ratio anyway. So opposite is x, hypotenuse is 3, and we're looking for cosine theta because we're going to cube it here and keep it regular here. So to fill in this, because that's the ka part, adjacent over hypotenuse, this is going to be the square root of 3 squared, which is 9 minus x squared. And if you want to add an intermediate step here to do like a y squared plus x squared is 3, and then solve for a positive length, you can do that. Doesn't matter, however you like it. Either way, you get cosine theta is the square root of 9 minus x squared all over your hypotenuse. So this looks complicated, but basically we're trying to go from our sine theta to cosine theta so that we can plug into this so that we can get x. So I'm going to plug this thing in. So we have cosine theta is this, but we're going to cube it. So we have 9 minus x squared over 3. We're going to cube it, put it over 3, minus square root of 9 minus x squared over 3, all plus c. Nice job. Awesome. So now we're just going to clean it up. There's a bit of algebra work, I'm going to distribute this 27 back in just to make sure that we match with the other method, the U-substitution method. So I'm going to try and write it in the exact same form, or at least something similar, just make sure that we got the same answer. So if I do 27 divided by 3, I have a 9 here, and then I have to cube this, so I'm going to rewrite this as 9 minus x squared to the 3 over 2, because this is 9 minus x squared to the half cubed. So 3 over 2, I still have an over 27. Whoops, I didn't cancel that. And then I'm going to rewrite this as a 9 minus x squared to the half over 3 plus c. And just last step, I'm going to cancel that out. And so we get, oh no, I distributed the 27, so this actually should be a 9, and then, my bad, so the final answer will be 9 minus x squared to the 3 over 2 over 3 minus 9 times 9 minus x squared to the half plus c. And I am praying that this matches what we got before. Let me check that. So we have 9 minus x squared to the 3 over 2 over 3 minus 9 times 9 minus x squared to the half plus c. Okay, good. So hopefully, since we did it 2 ways, this is definitely right. But if you really want to check, you can take the derivative of this or this, and it should be algebraically equivalent to our original thing that we're taking the integral of. This isn't actually too bad because we have something, the power of something, and as long as you remember to do the chain rule, right, we have to multiply by negative 2x, do each part, find a common denominator, and it should be this. One thing I wanted to point out was that notice that our answer from this long convoluted trig subway actually shows no sign of sine. So all of the intermediate theta stuff and the trig sub stuff, or the U substitution, doesn't show up in our answer. It was just a trick that we used to simplify the square root of this mess so that we can deal with just a trig integral, or some integral involving a trig function, which is just a bit easier to deal with. It gives us a direction for moving forward, and then we just have to go back and make sure we answer in terms of x. So I hope that this was interesting. Obviously this side is much simpler, but that goes to show that just because if you're learning trig sub and that's the newest and latest and greatest tool to add to our math caboodle, that's not necessarily the only way to do it. We can still combine some algebra techniques, we can combine integration by parts and all of that. So just becoming confident about that just kind of comes with practice and having fun with it. So thanks for joining me, and I will see you for more math very soon. I'm sending you lots of love, and if you are asleep and bored by all of this, then I hope that you're having sweet, sweet dreams. Bye!